Welcome to this week's iCanX Talks. This is Paul Weiss from UCLA, stepping in for Alice Zhang, who's on vacation today, but is with us nonetheless. We're delighted today to have two speakers, Zhiyong Fan from Hong Kong University of Science Technology and Andrea Armani, just down the street here in Los Angeles at the University of Southern California. The theme for today is emergency engineering, translating innovation into impact. And I think you're going to enjoy these talks very much. First up, we have Zhiyong Fan from the Hong Kong University of Science and Technology. Professor Fan works across nanoelectronics, taking inspiration from biology, looking at, and his talk today will be Biomimetic Optoelectronics with nanostructures. And I think we're ready to turn over the mic to Professor Fan.
All right. Can you hear me well?
Yes.
Thanks, Paul, for your nice introduction. I'd also like to thank Alice for sending me a warm invitation. Otherwise, I won't be able to share with you guys our research. Meanwhile, I'd also like to thank Alice for organizing 16 series of the online seminars already. I benefit a lot, I learned a lot from the past seminars. I know it's not an easy job under such condition. So Alice has done a wonderful job to assemble a team of the top research scientists giving speeches on different research fields. Today it's my great honor to join them and share with the audience about our recent research on the biomimetic optoelectronics using the nanostructures and the nanomaterials. So here's a brief outline of my talk. I will start with a brief introduction. What is biomimetics? And then I will give a few examples. So what we have learned from Mother Nature that give us the inspiration to build the materials and devices that can be functional. Then I'll spend most time focusing on introducing our recent research on the nanowire array-based biomimetic retina and artificial eye. So I'll end my talk with providing some future perspective, more on the application side, and how our biomimetic eyes can help us in the future. Okay, so biomimetics is not a brand new research field. It's a known field. I think what is really new is we keep learning from Mother Nature to solve our new problems, to enable new technologies. So these will be new, okay? So if we search biomimetics on Wikipedia, here I also provide a Chinese version of the definition. It's just one single definition. But in English, we have two words. One is biomimetics, the other is bionics. So in most cases, these two words are interchangeable, but there are subtle differences. So from the definition, biomimetics or biomimicry is imitation of the models, system, elements of nature. Let me switch to the laser pointer. For the purpose of solving the complex human problems. And the bionics or bio-inspired engineering is application of biological methods and systems found in nature to the study and design of engineering system and modern technology. So actually bionics, this work came out a bit earlier than biomimetics. To me, the difference is the biomimetics is more on the imitating the nature, materials, or the devices already existing in Mother Nature. And bionics is more like we got some idea, we learn from the nature and use that idea to solve our problem. Okay, so I think I mentioned that it is not something brand new. We use that to keep solving our problem, old problem and the new problems. I want to give you an idea or give you a very brief introduction how we benefit from biomimetics in the past, I'll say. So since many thousand years ago, we are still running on the ground chasing other animals. We see the birds, the eagle, flying freely in the sky, right? So that gives us a dream to fly like a bird in the sky freely. We want to have a wings, but of course, we can't do it unless we're in the dream, right? But people are smart. There are many smart people in the past. So first version flying object or aircraft is kites. About 2,400 years ago. Okay, so it has been invented a long time ago. For example, this very famous engineer and scientist called Lotus from mainland China. So he invented this kite. It took him like 3 years to brought it to the sky. Okay, so about 2,000 years later, Leonardo da Vinci. So he's also very famous artist and engineer and inventor. So he designed a number of different kind of flying machine, aircrafts, but they all remain on his drawing because no power, no engine. But if you look at this flying machine, it's quite similar to the eagle, right? So it had a pair of wings and has a tail. So it was Da Vinci's vision that one day, if this flying machine is equipped with engine, it will fly in the sky. 400 years later, Brother White installed the diesel engine on the biplane. So for the first time with engine and propeller, they put the airplane in the air. So this is a breakthrough, okay? And nowadays, we are all traveling around. Before the pandemic, we're always traveling around the world with commercial airlines, okay? The many companies, Airbus, Boeing, also China also has a commercial airline company, but that was before the pandemic. I really missed the time, okay? But anyway, if you see it, the shape is still very much look like bird. It's a pair of wings, it has a tail and rudder. Not much change. The aerodynamic hasn't been changed for 1,000 years. Even we have a supersonic aircraft, even we are much, much faster than a bird, but still it looks like bird, okay? So this is I think this is a perfect example that we learn from the bird. After 1,000 years, we can fly freely in the sky. And now we're flying out of Earth into the space. Okay, I want to give you several other examples more related to photonics and optoelectronics, which is my main research topic today. So first creature is a butterfly. So we all appreciate the beauty of a butterfly. You look at the wings, colorful, blue, red, or other colors. If you magnify the butterfly wing with an electron microscope, you will see the multiple level of nanostructures, from a few nanometers, tens of nanometers to a few micrometers. So these nanostructures, they have a capability to manipulate light, reflection, diffraction, transmission, etc. With that capability, we can control the color of the butterfly wing, or the butterfly can control the color of its wing. The second example is a dragonfly. We all know dragonfly is so agile, it's very difficult to catch it. So one of the reasons for its agility is because it's a very powerful compound eye. So you can see, this is also zoom in photo of the compound eye. So dragonfly is a pair of the compound eye, spherical. They have almost 360 degrees of field of view. So you can see any threat from any angle. So it's, of course, very difficult to catch it. Well, the third example is our human eyes. So the human eyes connect our soul, especially in these days. We all walk out with a mask. Out of our home, out of office, we walk on the streets, we always wear our mask. How do we recognize each other? So through the eyes. So this is a very special time. And the eyes our eyes have very complicated or elegant structure, very elegant device structure inside. It's very dedicated. That will be the main topic of today. So I will give you more detail of human eye. Okay, let's first look at what can we do. What can we, after we learn all these natural structures, what can we do? So the first example is we can mimic the structures on the butterfly wing, and we can build artificial structures that can control the color of the objects or any surface. Right? Depends on the pitch, the size, we can get different kind of colors, red, green, purple, etc. We can use this kind of nano gyroid structure, or we can use this multiple levels, multiple layers of the nanostructures to achieve different kind of colors. So this is called a structure color. The second case, the nanostructure not only can give us color, control the light propagation, but also it can sometimes bring us very unique functionalities. For example, this is the work we have done a few years back by my student, Kwang Hoi-Chor. So he invented this nano cone structures on the plastic. So he fabricated the nano cone structure on the plastic to mimic the function of the lotus leaf. So lotus leaf has this many microstructures that render the surface the super hydrophobicity. So basically, the water stays as a water droplet on the surface. It's very easy to move around, and if there are dust on the surface of the lotus leaf, so the water droplet will just move around and carry away the dust and maintain the cleanliness of the lotus leaf. So this is called a self-cleaning function. So Dr. Choi, he fabricated this lotus leaf inspired structure on the plastic film and attached the plastic film on the solar panel surface and the solar cell surface, and gave the solar cell surface hydrophobicity and also the self-cleaning function. So this is one example we learned from a microstructure for solar energy harvesting. Now let's look at the eye again. Let's start with the arthropod, the common eye from the arthropod. So if you look closely at the structure of the the compound eyes, you can see the many small eyes. We call that ommatidium. So one single eye, if you look at the detailed structure, on the top it has a microlens to collect the light, and in the middle, it has a channel. It has a waveguiding nature to guide the collected light down to the bottom. There's an image sensor. There's a photodetector. Okay, so this structure. Keep in mind this structure. One ommatidium. So the whole compound eye consists of many this kind of ommatidium or small eyes and distributed on a hemispherical substrate, so that it has a very large, like here, 180-degree field of view. So you can collect the optical signal from very broad angle. Okay. And here are the pictures of the world or the flower perceived by the compound eye. The world is pixelated, depending on the distance, because there are so many small eyes and small image sensors. That's why the world in insect eye is pixelated. But anyway, like I said, it has a very broad field of view. It's very beneficial for many technological applications. So back in few years ago, scientists, 2013 actually, there's a paper popular on Nature. John Rogers' work, this is. So his group assembled many photodiodes on a hemispherical substrate. Okay. Then this already, it is an artificial compound eye, can have a very large field of view as well. So one more thing we can learn from the compound eye is that there's a waveguiding structure, like I said. So last year, one of my postdoc, Dr. Qianpeng Jiang, he fabricated perovskite solar cell on this kind of a waveguiding structure. So we call that a nanophotonic LED device. So on the top, there's a nano dome structure, just like a micro lens that can collect the light and focus the light into the channel. So in the channel, we have the titanium dioxide waveguiding material. So this whole material the scaffold is aluminum oxide. It's a porous aluminum oxide. Or people call it PAM or AM. Anyway, it's aluminum oxide material. You filled up with titanium dioxide wave guiding material. Okay, so this whole structure helps to extract the light from the perovskite light emission layer and enhance the overall external quantum efficiency of the LED. And how much can it improve? If you look at the bottom right figure over here, the planar structure with this material, perovskite material, planar structure can achieve 8% external quantum efficiency. But with the optimal structure, we can achieve 17.5% external quantum efficiency. So that's more than double. So that shows this wave guiding structure, the powerfulness of this wave guiding structure that we can learn from the compound eye. So another interesting creature, another kind of interesting creature is a fish. It's in the water. A fish eye is also very interesting device. Fish eye always look like some hemispherical. It has a very large field of view. So just recently, two South Korea groups, they published a very interesting paper on Nature Electronics. So this is about aquatic vision inspired eye camera. So this is basically a fish eye camera. So the two research groups, they learned the fish eye structure and fabricate this hemispherical image sensor. So they perform this fabrication with a pattern transfer. They firstly fabricate on SOI wafer. On the SOI wafer, they etch the silicon nanorods, then transfer to the hemispherical substrate to form this hemispherical retina for the fisheye camera. Okay, so the fisheye camera can also image the pattern projected to the camera. It's very interesting work. So how about our human eye? So perhaps it will be more useful to mimic our human eye, and the application I can show you later. So our human eye is a single eye. So it has many unique features. Like, of course, it's spherical. It has a large field of view. It has very good sensitivity, adaptivity to the change of the light environment, light intensity. It has a good resolution, and the optical response range is 400 to 700 nanometers. Okay, so this picture in the middle showing the internal structure of our human eye. So the key component is this retina on the back. Okay, so this retina is very delicate. I'll give you more detailed structure later. Well, let's think again. So how important are our two eyes? So we have sight, hearing, smell, taste, and touch, 5 different senses. And among them, our brain acquires 83% of the information from our sight. So that shows the importance of our eyes, the major sensor, major signal input device for our brain. So our brain is like a computer process, all these signals, right? So if somebody lost the vision, blind, half blind, so it will be very, very painful experience. So what can we use? If we can build this bionic or biomimetic eye, what can we use it for? For many applications. So for example, for robotics, I myself is a big fan of all the sci-fi movies like iRobot, Terminator, and the recent Westworld, different version of the robots or cyborgs. So they all have the artificial eyes, just like a human eye. Okay, different kind of versions. Well, definitely, if we have a technology to build the artificial eye, we can use it for robots. And it's better. We expect it to look like a human. On the other hand, there are many, many people in urgent need for the artificial eyes. So here shows the data of the global population for the visually impaired. So globally, we have around 200 million people suffering from the blindness, half blindness, visual impairments. And this number is going up because these days we're interacting with the screen, electronics, photoelectronics so much that kills really our eyes. And really a lot of people, they are in urgent need for the vision recovery technologies. So what is the progress on the eye mimicking, biomimicking? Back in 2008, so there was a pioneer work also done by John Rogers. So his research group fabricated this electronic eye. So the process to fabricate it was basically the steel fabricated device on the planar structure, planar silicon wafer, and with a sacrificial layer at the bottom. So they release the structure and transfer to the PDMS substrate. So PDMS substrate was prefabricated as a dome, as a hemispherical structure, then stretch it, make it flat, then transfer the flat array of the silicon photodiode on it, then release back from the hemispherical photodiode array, then transfer the hemispherical photodiode array to the hemispherical glass substrate. So this is the whole fabrication process. It is a long and very challenging process. And they eventually built an electronic eye and demonstrated the imaging function. Okay, you can actually see the detail over here. They use this stretchable, they call it stretchable silicon. Okay, stretchable silicon interconnects, very useful. Well, the problem is not only that this fabrication process is very challenging. The sensor density or the pixel density is very low. It's about 1 pixel or 1 photodiode per millimeter square. So on our human eye, well, of course, we have very, very high density of the photoreceptors. So the question will be, how can we fabricate artificial eye with much higher resolution? We call that acuity. Eventually, that will give us, that will determine, how sharp the image will have in the end. And how can we make an artificial eye more similar, look more similar to a real eye? And the ultimate question will be, how can we build artificial eye that can even overperform a real eye in certain aspects? So to answer this question, let's firstly study a bit more detail of a human eye, especially the core component, the human eye retina. So here I'm showing you 2 pictures. The picture in the middle is a schematic of the retina, and the picture on the right is an SEM image of the cross-section of the human retina. So the thickness of our human retina is around 350 to 400 micrometers thick. So there are many layers. So the most important layer is the layer on the top over here, the rod cell and the cone cell. So these are the photoreceptors. These cells, once receive the optical stimulus, will generate the neural electric signal. Okay, so then lower than that, we will have other cell layer like horizontal cell, etc., bipolar cell, and the ganglion cell. So these are, you can consider as a signal processing layer. Okay, then at the bottom we'll have the optical nerve fiber layer. So this layer is like interconnects or signal transmission layer. All the neural electric signal will go into the optical nerve layer, then eventually go to our brain for signal processing. And the light will come from the bottom side. Okay, the light need to go through multiple layers in order to reach the rod cell and the cone cell over here. And maybe you already realize that it's not a very efficient way as a photodetector. Okay, because number one, the light has to transmit it through around 300 micrometer second in order before reaching the photoreceptor. So in this whole transmission process, there will be around 40% of the intensity loss. That's problem number one. So the problem number two is that, as you see that we have all those nerve fibers on the front side of the retina. In order to go to the back side of the retina, they have to go through a bundle of the optical nerve fiber. They have to go through a hole. There's a hole on our human retina. Okay, so inside this hole, there's no photoreceptor. Okay, and that's why we have a blind spot issue with our own retina. And you can find an experiment online how to find your own blind spot. That means any subjective image fall on this blind spot, we can't see it basically. So normally people say just our human retina is an inverted image sensor, but not all the retina they're inverted. Some low-level animals like cephalopods. Okay, very interesting. So these creatures are living in deep ocean, like squid, octopus, etc. If you look at their eye design, retina design, It's actually more logic than our design. Now, there are optical nerve fibers that behind the retina. Okay, so they're photoreceptor on the front side. So with this design, they don't have the blind spot issue. And they also mitigate this light loss issue. Okay, so light can just directly reach the photoreceptor. They don't have to go through this nerve fiber layer. Now you can see, we think we are the high level, more advanced creatures, but our human eye design is not as good as the Sci-Fi parts, right? So is that a joke or something? I don't know. And there's no consensus why this happened, okay? So just my personal opinion. Maybe because all these kind of creatures, they have to live really deep in the ocean. So the surrounding optical environment is really, really weak. The optical signal intensity is very, very weak. In order to survive, they have to evolve into very powerful eye design structure. It's just my personal opinion, okay? All right. So if we have a second look of the retina structure, we can see we have this three-dimensionally assembled, integrated raw cell and cone cell that look very similar to our nanowires. We made many nanowire arrays in the past. So this is a cross-sectional SEM of nanowire array embedded, three-dimensionally embedded in a porous template. So that gave us the similarity and inspire us. Why can't we just use a nanowire array to mimic the raw cell and the cone cell? Because both of them can generate electrical signal, photoelectric signal. So I want to give you a very brief introduction or background information about how we fabricated all these three-dimensional nanowire arrays. So we actually spent quite a long time. For myself, I started even when I was a graduate student in UC Irvine. I worked with my lab mates and day and night and try to find a way to assemble three-dimensionally all the nanowire structures. Eventually, we found a very interesting template. So this is not something very expensive, okay? Porous aluminum membrane. So it has many, many nanochannels, many holes, okay? The hole size, the depths can all be well controlled. So I'm showing you the SEM picture here, right? So we made this in so-called nanowire structures with well-defined the pitch and the arrangement, the ordering. Besides, the porous alumina itself is aluminum oxide, so it's an insulating material. If you assemble any electronic or optoelectronic material inside, you won't have leakage, electrical leakage or shortage problem. And because the material does not absorb light, it's a wide bandgap material, right? Does not absorb the visible light. So it won't interfere. It won't generate any parasitic light absorption for the visible band optoelectronic device. And of course, itself is a very mechanical robust and chemically stable. So all these merits are really making us believe that this is a very good platform to integrate all the optoelectronic or electronic devices. We have done a lot of work based on this material scaffold, including the LED, including the solar cells and also the photodetectors. So talking about the photodetectors, so my postdoc and my student, Dr. Lei Gu and Walid, so they work on integration of the perovskite nanowires into the three-dimensional this porous template. So in 2016, they published a paper on advanced material demonstrating that they can grow. We use the CVD, chemical vapor deposition method, to grow the perovskite nanowires into the array of the holes. So here you can see the top view. And all the nanowires, they are well arranged in the hexagonal ordering. The pore size, the nanowire diameter can be well controlled. And also the nanowire height can be controlled. So the chemistry, I don't want to spend too much time because I have time constraint over here. Basically, two-step reaction, we got the perovskite MAPBI3 over here. And we also explored how we can fabricate the device. And we figured out that we can just delaminate the very thin layer of the three-dimensional nanowire array and transfer to flat substrate. This is a flat substrate, and we put the top and bottom electrode. Then we made image sensor over here. So this is the image sensor we made, and with 1024 pixels. Okay, so outside we have this ribbon cable, we have a multiplex and computer to apply signal. So this whole thing can acquire the optical image projected on it. So through this project, we actually figure out how we can grow this three-dimensional nanowire array inside the porous template. But that was on the flat substrate. The biggest challenge is how we can make this hemispherical or 3D nanowire array, because our retina, the core component here is hemispherical, right? So how can we fabricate hemispherical nanowire retina? And how we can make the contact, front contact and back contact, because it's no longer planar. There's no conventional existing method allows us to fabricate electric contact on non-planar substrate. And if we can achieve it, how can we integrate other parts into a spherical eye, artificial eye structure? So all these are big problems. We've been thinking for a while. I've been thinking for like close to 5 years on how to solve that problem. But eventually we found that it's actually not very tricky to do. So if I explain to you, you see it's quite straightforward. Why? Because we start with aluminum. I demonstrate that we can use aluminum from the aluminum oxide, porous aluminum oxide. So it turns out if we can just mold aluminum, because aluminum is soft metal, right? We can just mold it and form this bowl-like structure, hemispherical structure. We can use the mechanical molding. It's quite easy to do actually. Then we can anodize this hemispherical aluminum bowl. Then on the surface, inner and outer surface, we will have this hemispherical porous aluminum membrane with many, many holes. And inside the hole, we can repeat what we have done, grow the perovskite or other nanowires, and we can get the nanowire artificial retina. So it really took us some time to get to this stage, but eventually, it turns out it's not a very difficult thing to do. And here at the bottom, I'm showing you a few pictures of the nanowire retina. On the left and in the middle, you can see the black color, because here we grow the perovskite FAPVI3 perovskite nanowire into it. It is a very strong light absorber, so that's why it's a black color. On the right-hand side, you can see this cross-sectional image, SEM image of the nanowire retina. So it is a hemispherical structure. Okay, so with that, we can build our artificial eye. We already have the key component over here. Here, I'm showing you the comparison between the real human eye and our artificial eye. And particularly for this retina, it may appear similar to the human retina, but we have a way to fabricate the bottom, the front side and the back side electrodes. So I will explain how we do. So all we want to do is we want to avoid this blind spot issue. So here's a detailed structure of our biomimetic eye. So the core component is still here, the nanowire retina. So how can we achieve the contact? This is something also bothers us for a long, long time. And eventually we figure out how to do. So on the front side, we just put on, well, we drop this ionic liquid. So ionic liquid is a liquid, of course, right? So it doesn't have a water, it's not aqueous, so it won't attack the perovskite material. So this ionic liquid can conduct electricity, can transfer charge from nanowire to the contact electrode. The contact electrode is a metal shell, hemispherical metal shell, which has a hole. We can assemble the lens over there. Okay. So the ionic liquid, since it's a liquid, so it can diffuse into the channel and reach the nanowires. Okay. So here, figure E shows a cross-sectional image, SEM image. You can see the nanowires are perhaps 3 to 5 micrometers long, and there's a channel over here. The depth of the channel is around 50 micrometers. So with the ionic liquid, the liquid can diffuse into the channel and reach the top surface of the nanowire. So with that, we form the front contact. And also because it is an ionic liquid, it's a liquid, it mimics the viscous humor inside our human eye as well, which used to provide a pressure to stabilize the eyeball structure. So how about the backside? So since the front side, we already have a common contact. So from the backside, we have to have the pixelated contacts. So we actually use the This is liquid metal fibers. So liquid metal fibers mimicking the optical nerve fibers in our human eye. So basically we use the indium gallium material we inject into the rubber tube, very thin rubber tube. It's a bit less than 1 millimeter. And we assemble all these liquid metal nerve fibers in a socket. So this is artificial socket. So this socket is made by PDMS. Okay, PDMS is flexible. Many holes you can see over here. We can use this hole to assemble all these liquid metal fibers, and then touch the bottom, cover the bottom side of the retina. Okay, it's easy to say, but it also takes some time to really get, the optimum point, the pressure, etc., to get a very good electrical contact. It's not an easy thing. Okay, so this slide shows how we fabricate this artificial eye socket. Basically, we first use a 3D printing to make a mold, and we cast the PDMS on it with many holes, and we can assemble the whole eyeball together. And the working principle of our artificial eye, or biomimetic eye, so we can firstly measure one single pixel over here. So these are in the middle, there are IV curves or CV curves. So this is mostly for the electrochemical measurements. Basically, it is an electrochemical device or electrochemical photodetector. So my student, Dr. Yuanjun Lin, she figured out the working principle of this eye, so electrochemical principle. So the working principle is kind of similar to dye-sensitive solar cell. Okay, over here I have some drawing over here that shows how the charge move from one side to the other side. Basically, here we rely on the triode and iodide redox reaction to move the electron move the photoelectron from nanowire ionic liquid interface to the working electrode and flow out, and then we form the external photocurrent. So this is the working principle in short. And how about the performance of the biomimetic eye? Here on the top, I'm showing you the response speed. So in figure here, you can see the response time is about 32 milliseconds. So you can see with the light on, the current increase. It doesn't matter the sign, but the magnitude increase, right? And the recovery time is around 40 milliseconds. So in the best case scenario, we can tune we found this response time largely depend on the composition of ion and liquid and concentration. So if we increase the concentration, we can get an even faster speed. So tenths of a millisecond is not very fast compared with a solid state device, right? What's the reason? Because we have to have this charge transfer through the ionic liquid. So this is the speed limiting factor. But compared with our human eye, our human eye, the response time is somewhere around 50 milliseconds to 150 milliseconds. So it's not very fast anyway. So compared with the human eye, it's already fast enough. So how about sensitivity? We found the photocurrent versus light intensity curve is quite linear, log scale, of course. So the lowest light intensity we tested was 0.3 microwatt, 0.3 microwatt per cm squared, which is about 0.1% of our indoor light illumination at the nighttime. And on the bottom right, you can see the wavelength response range. Because we use the FAPBI3, the cutoff wavelength is around 800 nanometers. So the device can respond roughly from 300 nanometer, a little bit of UV, and to 800 nanometer wavelengths, which is already broader than our human eye. Our human eye's optical response range is from 400 to 700 nanometer, this range. Of course, it also depends on the material we chose, right? If we choose to use a smaller bandgap material, there are many choices of smaller bandgap material, like indium antimonide, for example. We will have a much broader range of the response, and including some IR. So after testing the individual pixel, then we can actually perform a system level test. So system level test, you can see here we have a PCB board. We assemble all these ionic liquid fiber, and on the PCB board, so the ribbon cable goes to the multiplexer. So multiplexer control the channel, which channel is turned on for the measurements and scan pixel by pixel, we can acquire the image we project onto the eye, the artificial eye. So so next time I'm going to show you a video how we perform the measurement. But anyway, so the field of view we measure over here is around 101 degree, which is already much larger than the camera on our cell phone, which is around 50. Human eye, for your information, human eye, the field of view is around 150. So, but there's still room for us to improve. I think we can increase to that level if we can optimize our eye design. So here is a slide. Let me see how I can play this one. Here is the video. Here is the video. Okay. So basically, we have a projector over here. So projector controlled by the computer. So computer is outputting the PPT to the projector, and the PPT has the pattern. So the projector projects the pattern into this biomimetic eye. On the backside, we have electronics to acquire the signal. This signal will go back to the computer to generate the image. So let me play this. Okay, it's generating letter E and acquire letter E and the EYE. Okay, so I think that gives you an idea how we perform the measurement. But you can see this is still very much pixelated, right? Because we have only 100 pixels, 100 liquid metal fibers. So this is very, very difficult to assemble so many on such a small eyeball. Like I said, the diameter of each liquid metal fiber is around 1 millimeter. So the pitch of the pixel is around 1.6 millimeter. So which is very large, right? How can we further improve the resolution? That's the thing that the reviewer also challenge us. So to see the limit, another of my students, Swamana D. Ponda, who came from India, my PhD student, he spent a lot of time on making one single nanowire or a few nanowire based the sensor, image sensor, or photodetector. So he used a focus on beam to drill a hole on the backside of the porous alumina. The porous alumina, the backside is covered by the aluminum oxide barrier layer. And he drilled one single hole over here, open one single channel, then grow one single nanowire into it. And on the top, we dropped on the liquid to form a circuit and perform the measurements. And indeed, one single nanowire can also respond to light. And we also made a 4 nanowire device. It can also respond to light, but of course, the magnitude is much lower. So here, I want to bring your attention. The density is of our nanowire photoreceptor is really, really high. So the pitch is around 500 nanometers. Okay, so with this density, is already even higher than the photoreceptor inside the eagle eye. Okay, so it can potentially have a very, very high resolution as long as we figure out how to address each individual nanowire electrically. So how can we do that? As I mentioned that the liquid metal fiber is too big. We can't make a pixel very small and pixel density very, very high. So then we've developed another method to increase the pixel density and reduce the pixel size. So this method is not focused on beam anymore. So it is more upscalable. So basically, we fabricate on the backside of the photosensitive nanowires, we fabricate the metal nanowires and use RE to expose them out. So then we form a metal nanowire forest. You can see figure D, many metal nanowires sticking out from the surface of the porous aluminum. And then on the top, we assemble the microneedles. So these are the nickel microneedles. Okay, so nickel wires, we can choose a diameter. They can be like 20 nanometer, 10 nanometer, 100 nanometer. And we can sharpen the nickel wire with the electrochemical action, make it really sharp. If we place one single needle on the metal nanowire array, we can achieve the condition that one microneedle touches 3 nanowires. Then we'll form around 1 micron pixel size, very small pixel. Then the pixel density will be determined by the nickel nanowire diameter, which can be very small. And how did we do the assembly of the microneedles? We actually use a magnetic field. So like here I'm showing you. So we place a big magnet under the substrate. And once we turn on the magnetic field, these nickel microneedles, they can stand up on the nanowires pretty well. Okay, so this is how we assemble them. Here also one short video. Okay, so in this video, at the bottom we have an electromagnet, and this black color chip is our nanowire array. And we already assembled many needles, and let me see. It's a very fast process. Okay, so once we turn on the fuse, the needle will drop. Well, in reality, we drop the needle more gently than this. Okay. Okay, so with that, we can fabricate a very small size of the pixel and also high density. And we fabricate a very small camera or very small image sensor. How small it is about a 2 millimeter by 2 millimeter. On this 2 millimeter by 2 millimeter size, we assembled 100 electrodes. So we make a mini camera. So this is a sensor, the core in the middle part. You can see there's a hole. The hole is a reservoir for the ionic liquid. So the image sensor is right in the middle of the hole over here. Then we put a whole image sensor into the mini camera. So this is a coin over here. The camera itself is very small. It has a 100 pixels. Then we perform the measurement of our mini camera and micro needle based mini camera. So each single pixel can also respond very well to the optical inputs. And we can also image the pattern. So this is the letter E. We project it to this image sensor. And this image is very small. Like I said, it's 2 millimeter by 2 millimeter. And we did a manual assembly of this needle, so we couldn't do a lot more than that. You may ask, so this kind of device is still planar device. So can we fabricate those micro needles back contact on the hemispherical NW Retina? Oh, here's a video. Well, even let me see. So here we have a magnet. Okay, we have this ferromagnetic material ball over here, and we cover with our hemispherical NW Retina. And once we turn on the magnet, this magnetic field, we actually simulate the magnetic field. They come out, from this surface of the magnetic bar. And you can see with just a little bit of voltage and the current, we can assemble very well. We can assemble all these nickel nanowires, nickel microwires very well on the surface of this hemispherical surface. Right? If we lower the voltage below a certain point, you see it is start to shake on the hemispherical retina. Let me see, maybe, yes, like 1 volt. So it turns out it doesn't really need a very high voltage or high current to fix all these micro needles on the surface. Right? So next step is after we fix them. So because there's a contact pressure over here, so there will be very good electrical connection between the microneedle and all this nanowire array over here. So next step is we can drop some epoxy to fix and package all these microneedles on the surface. Okay, so then with this method, we can form the backside contact. And of course, if we do manual assembly of all these microneedles, we can't get a very high density. Then we can use robotic arms in the future, right? So these robotic arms, they can have very high precision, like 5 to 10 micron precisions. Then we can have many electrodes, and that can increase our pixel numbers. Okay, so above are the main contents of my presentation, and here I want to share with you guys some of our thought on the future application. And of course, the curved image sensor very important. It has a very large field of view. It can be used for cell phone camera or surveillance camera or the machine vision, right? But after our work was published online. Many people visually impaired, they contact with us and ask us, so when can they benefit from this technology? Okay, then we look into the detail of this retina implant. The market is really, really big. This shows the need is very big. Okay, so perhaps we don't have to replace the entire eyeball. If somebody damaged if somebody is visually impaired but not but the damage may be onto this retina, okay, maybe especially on the photoreceptor. So we can perhaps just use our nanowire array, our artificial retina, to replace the photoreceptor. Either we put on the front side of the retina or on the back side of the retina. We can help to recover the vision by using the nanowire array generate the photoelectric signal to stimulate these neurons or these degenerated photoreceptors. So there are existing technology in the market. Okay, so there are two technologies, mainly two technologies. One is Argus-2 technology. So in this technology, the engineers use this micro-electrode array. These are the metal electrode array. They mount this micro-electrode array on the front side of the retina over here. But the electrode array here does not generate the photoelectric signal. It relies on the goggle being worn by the patient. The goggle has a camera on the front side. So the camera generates image and transfer to these wireless antenna over here, also on the goggle. Then through this wireless communication, the image or the photoelectric signal transfer to the electronic case, wrap around on the eyeball, then go to the metal electrode array. So it is a long process. And it's also a very painful process for anybody to wear this. Imagine you have to wrap around the eyeball with something, right? It won't be very comfortable. And the chip is very small. It's only 3.5 by 5.7 millimeter. It cannot be very big because it's a planar device, right? Our human retina is hemispherical. If it's very big, and it cannot attach very well on our retina. So only has 60 pixels, right? 60 pixels cannot give us any image. Can only tell us whether there's an object in front of us or not. So the other technology from Germany is Alpha IMS. So basically the technology here is very different from the first technology I mentioned. They put the image sensor on the back side of retina, really right next to the photoreceptor layer. Okay, so this image sensor itself has amplified to amplify this photoelectric signal, provide a voltage signal. And because this one is very close to the photoreceptor, so they can actually use a higher density of the pixel array, interact with the photoreceptors. They have over 1,500 pixels. However, again, this is based on the silicon technology. So it is flat device, so it cannot be made very big. Otherwise, it won't be able to assemble on our retina, okay? So because it's very small, then the field of view is very narrow. It's only 11 or 12 degrees, so very, very narrow field of view. So there are only these two technologies in the market. And not many people are adopting this because the process is very painful to implant them and also very expensive at the same time. So if we can use our artificial retina, because our artificial retina itself is hemispherical, if we can replace this existing either the electrode or the image sensor over here and place our artificial retina either in the front on the front side or the back side of the retina, we have a chance to form very good contact with human retina. That can increase the area, increase the field of view. And also because we have very high density of nanowires. So potentially the hemispherical nanowire-based retina can provide a higher resolution of the image. So what if somebody, the eyeball got damaged, entirely damaged? So this is the wild idea I want to share with you. I also discussed with brain doctors and life scientists. They think there's a possibility. So here, we kind of are proposing a artificial eye-brain interface over here. So we have this hemispherical, we have this eyeball, our artificial eyeball is spherical, okay, with many fibers over here, electrical connections. And all these electrical connections can go to a metal electrode array. It doesn't really have to be rigid, it can be soft. But many people are already building this flexible contact to the brain, the visual cortex over here. So if we can deploy the micro-needle array on these vision cortex over here, so the artificial eye generate photoelectric signal, can stimulate this brain, the visual cortex. There might be a chance to generate the image, help people to partially recover the sight and the vision. So this is just a wild idea. I don't know whether it's possible or not. It may take 10, 20 years. Who knows? Okay, so here's a summary. So I think firstly, I introduced the biomimetics and hope I can convince you that the biomimetics really can open up the many different kind of possibilities for us to design the novel type of the optoelectronic devices, not limiting to the eyeballs, and can also be LED or other devices. So in my personal opinion, I think the biomimetics, we should combine the science, engineering, and the aesthetic together, okay? And here we use many different kind of nanostructures, right? Actually mostly nanowire or nanorod structures. So we call that biomimetic optoelectronics with nanostructures. I know people are using this concept to build the optoelectronics, but we're using the nanostructures because after all, many biologic structures are nanostructures. So talking about the nanostructures, and I think I introduced one way we assemble them, right? So we assemble them in a porous template so that we can achieve very high density, and each individual element, they won't short to each other, right? So we use this porous alumina template. So we call this optoelectronics on the nanoporous substrate. In short, it opens because it opens many opportunities for us to fabricate all different kinds of devices. So this is mainly about how we can implement the idea we gain, from the nature, the biomimetic device we want to build. How are we going to build? We can use this kind of technology to build. Okay. So in the end, I want to thank my students and postdocs. I have mentioned many of them in my PPT. So this is my group in Hong Kong UST. So this is the core team contributed to the artificial eye work over here. And I also want to thank our State Key Laboratory of Advanced Displays and Optoelectronics, led by the Professor Qing Tan, who is inventor of the organic LED. So in this State Key Lab, we perform a lot of research related to the light emission material, display technology, PV, and the sensor technologies, etc. So with that, I want to stop right here, and thank you very much for your time and attention. Thank you.
Thank you so much. Terrific talk. Let me get this screen up. And share. Oh, I didn't share yet. There we go. Well, that was fantastic. We have a series of questions for you lined up, and then we'll have a panel with Professor Armani. Let's start with the first question. Professor Fan, very impressive work. I'm curious, is this biomimetic eye black and white, or can it also detect different colors?
Thanks for the question. So far, our biomimetic eye.
You may be muted.
Can you hear me? I didn't mute myself.
Can we hear you?
Yeah, can you hear me? Okay, so I can be heard. So thanks for the question.
Yeah.
At this moment, our biomimetic eye is still black and white. We only respond to the light intensity. Only
there we go. Very good. Yep. Sorry, it's my volume.
So yeah, I'm saying that our biomimetic eye at this moment is still black and white. It generates a grayscale picture. We're still thinking how to make it, colorful. So we're still thinking. We haven't figured out how to do it. It may take maybe another 3 years to make a colorful biomimetic eye. We welcome to collaboration. If you have any good ideas, want to collaborate with us, we'll be very happy to work with you.
Very good. Second question. Hello, Professor. How can the material be made hydrophobic? By what do you apply to make that happen?
So we need to start with a material which is hydrophobic. Then we can make it super hydrophobic. Take PDMS as one example. So it's a water contact angle on the flat PDMS is already over 90 degrees. So in that case, we make into microstructure or nanostructures that can further increase the contact angle over 150 degrees. So that's beyond the threshold of being super hydrophobic. So basically, we start with a hydrophobic material first. And of course, there are other ways to make a material into hydrophobic, like surface assembly of a monolayer, fluorinated monolayer to make it hydrophobic, etc. That can also be applied.
Very good. The next question, Professor Fan, great talk. I sense a theme here. I want to ask, how do insects regulate so many omatidia?
So inside brain, if you count these omatidiums, each insect perhaps has a couple thousand, okay, a few hundred to a few thousand. Compared with a human, we have a few million photoreceptors. We have a lot more. The insect, they have a very small brain. They can process a couple thousand photodetector signal at the same time. They still have this capability.
Mm-hmm. And our next, and also what is its regulatory mechanism? How does that differentiation work?
I'm not entirely clear how inside they regulate all this signal, but from what I learned, it's also signal processing in parallel.
Mm-hmm. Actually, I'll before we go on to the next question, let me ask something related. In the work that you've done, what has the most difficult part of the eye been to mimic? So you've basically taken apart the structure and function in different ways, and both in terms of thinking about how to do it, and then design and making it happen. What was the hardest part so far?
The hardest part is a key component, human retina. So that's of course, the hardest part. And the hardest part of the hardest part is it's hemispherical. So it's horrible. So for fabrication, all we learned in the past was how we can fabricate device on planar substrate. So once it turned into 3D, it turns into curved substrate. So it's a nightmare for fabrication. So it took us a really long time how to fabricate the active material on the curved substrate and also figure out how to place the front side and the back contact. So this is the most challenging part.
Very good. And our next question, biomimetics can bring unique advantages to optoelectronic devices. Are there real products in use? You showed a couple examples with the second sight and so forth, but I would say maybe beyond just directly trying to replace the eye, are there other examples?
Yes, there are some applications. For example, this called mouse eye screen. In some computer, in some manufacturers, they apply this mouse eye screen. It's basically a nanostructured film attached to the computer screen to achieve the anti-glaring function. So like if there's a light behind me shine on the screen, right? So this microstructure will scatter light. It won't reflect the light into my eyes. So this is the one typical applications, but it's only small application, you know.
Yes. Do you see more coming?
I hope so. I see some cameras, fancy cameras taking like a fisheye design.
Very good. And then the last question you touched on a bit during your talk, but let's maybe give you a chance to explore that more deeply. That was just as you were finishing up. Human vision is powerful, but not just because of the eyes, but also the brain. You've achieved excellent sensors mimicking eyes. What are your ideas on how to mimic neural networks and the brain?
Well, this, well, this is a bit going beyond my expertise, but we are always willing to learn. Some of my students are working on the neuromorphics, and I'm also learning it. And some of my students are also working on this deep learning and artificial intelligence, dealing with the sensor arrays, not necessarily the photo sensors, but also other kind of sensors. So once we have many sensor signal comes in, then we have to do the signal processing, right? If we can learn from the neural network, neural network, how the brain works, it can really improve the efficiency of our signal processing. So this is something we started and we're still working on it.
Very good. That was just terrific. Now, under normal circumstances, we'd all be together and we would have a plaque for you recognizing the talk that you gave today, connecting the world in science. And so, I want to thank you on behalf of Professor Alice Zhang and her team and all of us who helped put together ICANX for this really beautiful talk. What we'll do next, yeah, so 300,000 people are clapping right now in their homes. Next, let's bring Professor Andrea Armani on, and we'll have a panel between the two talks before we move on to the next one. And so I think I stopped sharing my screen here. Mm-hmm.
So, Paul, you have to share.
Oh, share for the next one. So sorry.
Yeah. Well, you have to start my video.
Oh, here. And that should be
yes.
Okay. There we go. Sorry about that.
Okay.
Okay. So let me introduce Professor Andrea Armani. I'll give her a formal introduction before her talk, but she's a distinguished professor in chemical engineering at the University of Southern California, where she holds the Ray Irani Chair. And we'll tell you a little bit more about her when we get ready for her talk. But one of the more interesting things about her and where we'd like to start the panel is that she brings many high school students into her work. And so we wanted to ask how you are able to engage high school students in science and technology.
Yes. So first, thank you for inviting me today. Professor Fan has already had a chance to say that. So I invite high school students and undergrads into the lab, I would say for two reasons. First, high school students and undergraduates, especially high school students, they don't, at least in the US, many of them don't really have a chance to engage in engineering during their high school curriculum. Perhaps they have the opportunities through extracurricular clubs, but they don't really see what engineering means in terms of the innovation component. They might have a chance to, learn, what Newton's laws are, but they don't really get to see what it means to explore. And so by bringing them into the lab and really teaching them, what it means to explore and discover, they can really become excited about the idea of getting a career in engineering. And so how I engage them in that process is to kind of team them up with a PhD student or postdoc who is first off excited to be a mentor, because that's always important, and have them develop kind of a symbiotic project where the high school student may do a small component, perhaps a measurement using a UV vis spectrometer, and it'll help the PhD students research. However, that being said, the second reason I do it is that high school students and undergraduates bring a certain energy and enthusiasm to the lab that older PhD students and postdocs often have forgotten. All of us are very fortunate to have our jobs and have our positions. We're given a lot of intellectual freedom to just explore and fail and try things. But sometimes when you're, 3 or 4 months into an experiment and you keep trying things and you keep failing, it can become very frustrating. And when you are working side by side with someone who it is their first time to be in the lab, and the idea of getting to use a microscope is the best thing they've ever done, that enthusiasm rubs off. And you're reminded that, just having the opportunity to fail should be, exciting. So having that teaming can also be incredibly positive on the PhD student's mental health. So that's like a huge second benefit for the PhD students and postdocs. And, me as well, but especially for the students.
Have you been able to keep up that connection and activity during the times now when it's hard to get in the laboratory?
I have actually. So I have a high school student right now, and his project is actually based, so it's an experimental project, and we actually have him building an Arduino-based UV vis spectrometer system that he's building at home. So the whole thing is Arduino controlled. He's using a 3D printer to print all of the components. We're having him do verification experiments using, food coloring and dye. We're using as a control test light source a simple laser pointer. Obviously, when we get back into the lab, we'll, upgrade the light source, maybe upgrade the photodetector. But he's actually getting, his hands dirty in the lab, so to speak, and learning a lot about Arduino programming and data analysis and rigorous controls and the scientific method. And he'd never worked with Arduinos before. And that's, it'll be a life skill, right? Like he will have learned how to program an Arduino. So yeah, we're keeping it up and not, forcing our high school students to just analyze data. Which can not be exciting. So,
Very
yeah.
Good. Let me ask you each, and then I'm actually going to come back to the students in your laboratory in a moment, but we'll start with Professor Fan. Knowing what you know now and what you're trying to do, how would you root your training? Many of the students who are watching us around the world want to know, based on our expertise, what we would have liked to have seen and learned along the way. And so maybe start with you about how you would now map your training in terms of field.
Me being?
You being, let's start with you in
okay.
High school heading to college.
Mm-hmm.
What field you would choose, how you would do a PhD and postdoc, and I'll ask you.
Okay. So I'm going to show my age. When I was in high school, programming was in BASIC. So computers were just kind of taking off. And during college, the idea of getting a computer science undergrad degree was a new degree. And some of the new computer science degree students were kind of made fun of for getting this, newfangled degree. Is it really a degree program? And looking back, I would have taken classes in the computer science department, learned some programming in a more formal manner as opposed to trying to pick it up on the side. So I definitely would have just gotten a more rigorous computer science education. So that is one thing I would have done differently. I also would have, so my undergrad degree is in physics. So it was very theoretical in that sense. I would have taken perhaps an electronics course, perhaps a machining course, just to try to obtain some more practical hands-on knowledge. So those are things I would have done differently. I'm still very happy I got a physics degree, very happy I got an applied physics degree, all of that. But I would have tried to supplement that with some programming skills, some machining skills, some more just hands-on type knowledge. So.
And Professor Fan?
Well, when I was in middle school and high school, I started to teach myself with physics, more advanced level of physics, because I was so much in love with physics. And also I wasn't in a very competitive middle school and high school. And I had a lot of free time to start off my own projects, like building the remote control toys. Many of our friends, they're very busy with studying other very competitive high school. I think I was lucky enough to have a lot of free time to explore my real interest. So fell in love with physics, and in college, I was also in the applied physics major. It was called physical electronics. So, because I love physics, I love the electronics, and it's very natural for me to choose the major. But unfortunately, I didn't really get a chance to work on the projects when I was in college. It was a very different cultural setting at the time in mainland. But anyway, so I know what I wanted to do at the moment. It was very good. That has driven me through the many years over here till now to perform as a scientific research. But I wish I had learned some chemistry during my undergrad study. All my courses were on the electronics and the physics and some computer science, but I didn't study any chemistry at all, even though my major was material science. I think I was unlucky. And now I'm teaching myself chemistry, and you have seen from my presentation, electrochemistry and chemical deposition, all this chemistry knowledge I learned from myself and also my students. I'm still learning. So if I can turn back the clock, I wish I would register some chemistry class when I was undergrad.
Very good. Yeah, I think one of the things that is common among experimentalists is when we grew up, we tried to build things, and maybe even more often we broke things and tried to fix them. And that taking things apart and putting them back together is it gives us a set of very useful skills in making experiments work, where all the different parts have to work. We saw that in your talk, that you're trying to make all the different parts mimic the function of the eye, and maybe even soon going deeper and into the brain. So that's maybe a good lesson for people who are raising children, and Professor Armani, for what you're already doing for the high school students in your laboratory. I was curious about that as to where your high school students have gone since working with you.
So a couple of them have gone to UCLA.
Thank you so much.
Yeah, you're very welcome. So I would say probably half of them go to Berkeley. For some reason, my lab seems to send a lot of students to Berkeley. Some have gone to, a couple have gone to Columbia,
And
and
in what field you're in?
so they're pretty much all engineering. Various, fields in engineering, but pretty much all in engineering. And the majority of them actually continue to postgraduate degrees, either masters or PhDs. But pretty much all in engineering, some mechanical, some electrical, some chemical. I think there was one industrial, but they all continue. I stay in touch with about 2/3 of them. So I know two of them have gotten married now. It makes me feel really old. Like I knew them when they were 17. They're married. Yeah. So no, it's great to see them like go out into the world and do amazing things.
Can I ask you a question, Andrea?
Mm-hmm.
When you have the high school student work around in the lab, do you worry about the lab safety?
So I don't, because they aren't wandering around by themselves. So they have a PhD student mentor who is like walking around with them. So I've had two undergrads or two high school students that worked for an entire year. So they worked both over the summer and then during the academic year. And for those two students, by the time they were in their third semester of working in the lab, like they kind of had a little bit of independence. And so I wasn't as concerned about them being alone. But we also constantly have students in the lab. They're never in the lab truly alone. And my lab is, I would say, medium size. So everybody knows each other. All right, like all the more senior PhD students, even if they aren't like the official mentor for that high school student, they're still gonna watch out for them, right? Like everybody cares for everybody else. They aren't gonna see the high school student walking around with a beaker of HF and not say anything because you care about your colleagues. Right. Yeah. So I'm not.
I'll say in our laboratory, our high school students undergo all the same safety training that everyone else does. They can't come into the laboratory until they do get that training.
Exactly. Yeah, our high school students.
Gone to USC, but the identical twin of one did.
Okay. Well, I mean,
sorry, yeah.
It's okay.
Both. Well, thank you so much for this panel, Professor Fan. Thank you for the lovely talk. And now it's my great honor to introduce formally Professor Andrea Irani at USC, where she holds the Ray Irani Chair in Chemical Engineering and Material Science. And she's a professor of biomedical engineering, electrical and computer engineering, electrophysics, and aerospace and mechanical engineering. She's director of the Northrop Grumman Institute for Optical Nanomaterials and Nanophotonics. She won the PCASE Award from President Obama through the Office of Naval Research, and among her many other honors, she was named a Popular Science Brilliant 10. She's known for material synthesis and optics for detection and for therapeutics. And she's also known, as you'll see, for her creativity, and as you've already seen, for her enthusiasm. So it's my great pleasure to introduce her. Let me move on to the next slide here. There we go. And so the title of her talk today will be Emergency Engineering, Translating Innovation into Impact. Welcome, Andrew, Professor Irani.
So thank you very much for that fabulous introduction. I'm going to